Good morning and welcome, everybody. Today, you are here for our sound and acoustic event, and we are in for a treat today. Teachers, I hope you guys are ready for a loud and fun day. Let's get this day rolling. We have the amazing Lauren Sawyer who's going to be leading your introduction, and we're not going to waste any time. Let's get to it. Lauren, are you ready?
Yeah, I'm definitely ready to go. All right. Good morning, everybody who's here who's here live, and hello to everybody who will be joining for the recording. Welcome to the Sound and Acoustics Lab Day. This is a lab that is very near and dear to my heart. I studied a bunch of acoustics in my postgraduate degree, and I really love learning about acoustics, and I think this lab is super, super fun. So this is your sound and acoustics lab, mitigating noise pollution. You guys are going to learn about sound and design a solution to combat noise pollution. Noise pollution is a very big issue, especially in a lot of busy roadways where there are a lot of housing developments. I actually grew up right next to a really big kind of highway. And one of the things that they had to do when they were building my neighborhood was make sure that they put walls all around it to dampen the sound coming from all those big trucks, so that it didn't impact us as we were just kind of going about our day. So the idea of mitigating noise pollution is super near and dear to me. I grew up next to a bunch of big infrastructure that was able to do this, and it's just kind of always been a part of my life. So before I go any further, first of all, I want to shout out Jerry Dawes at Archbishop Stepanak. He is there live today, and Joanna Cottle at Duval High School. Thank you guys for being a part of the ET staff and joining those schools live. And I also want to introduce myself a little bit, kind of talk about why I'm here giving you guys this intro. So, like I said, my name is Lauren Sawyer. I am a research engineer in San Diego. I work part-time for two jobs right now. I work at Scripps Institution of Oceanography, and I work at Leidos Innovation Center. And basically, this might not sound like it has a lot to do with engineering, but I work with autonomous vehicles. So vehicles that can go drive themselves, and they either go underwater or they sit on the surface of the ocean. So I'm an ocean engineer. I work with vehicles that go out on the ocean or fly over the ocean. And what I specifically do is I create navigation methods so that these vehicles can, given the information around them, decide how to move and what path to take. So I want to talk a little bit about what an autonomous vehicle is. It's a vehicle that makes decisions by itself, and it can use artificial intelligence, machine learning, or sensors to understand and make predictions about the world around us. And when you think of autonomous vehicles, I'm sure a lot of you, will think about the Mars rover on a completely different planet, had to be launched out of this atmosphere. This is actually autonomous vehicle I work with. This is a picture of what we call the wave glider, and it basically is a robot that looks like a ship, and it harnesses wave energy to move itself forward, and it collects information about the ocean around it. And this is actually the vehicle that I work with on a day-to-day basis. I create motion models to describe how it moves through the ocean so that we can better predict where it's going to be. And my kind of track of autonomous vehicles is I work with the sensors information. So you've probably heard a lot about artificial intelligence and machine learning, and I work in the sensors track. So basically, what kind of sensors go on it? We have different sensors. One of them is an acoustic sensor that I will talk to you guys about in a little bit. And we have, GPS on there. That's what this big orange flag is for. It's our GPS sensor. So we can always know where that vehicle is in the world around us. So my engineering journey, I knew I always wanted to work with the ocean since I was in high school. I was in love with the ocean. I would watch all of the marine biology documentaries. I soon found out in high school that I wasn't a huge fan of biology. So I was kind of confused. I'm like, what other avenues are there to connect me with the ocean that aren't marine biology? And I started taking physics and calculus in high school, and I realized that I loved engineering. And I was watching the premiere of Blue Planet 2, this documentary narrated by Sir David Attenborough. And I realized that someone somewhere had to build all of these vehicles that they were sending to the deep, dark depths of the ocean. And I wanted to be that person. So I kind of had this idea, not really understanding how I would get there or, what companies made these vehicles, but I was like, I want to do that. So that's how I started my engineering journey. I went to college at Penn State University. I studied aerospace engineering because I wanted to study how vehicles move through different fluids. Air is a fluid. And so by studying how vehicles move through air, I thought I could best apply that to studying later in life how vehicles move through the ocean. And then I got the wonderful opportunity to work with UC San Diego and get my master's degree here. And this is really where I was able to explore the field of autonomous vehicles in the ocean and what being an ocean engineer is. I am able to be on the cutting edge of research and new vehicle developments. This is the same picture of that wave glider that I showed you guys in this previous slide. This is an octopus that we found on one of our sensors after pulling it back up after a mission where it was deployed in the water for about 2 weeks. And this is actually me, and this is an acoustic sensor. So it basically lets out a loud sound at a certain frequency. And I'm actually taping on a couple of like mounting devices onto it so we can throw it to the bottom of the ocean. And so I will talk to you about what we use acoustic sensors for later in this presentation. So starting with some background information on sound. Sound is all around us, and a sound you might enjoy hearing is music. String instruments are a great example of the physics of how sound moves and propagates. You're listening to my voice right now, and that is sound. So it's really anything that sends a pressure wave through the environment around us that our ears can pick up and receive as sound. So in this breakout, you guys are going to learn some fundamental information about sound and noise pollution. And then you'll be designing and building a noise barrier. And that's what you guys are going to be testing and iterating on. So you guys are going to build your first design of a noise barrier, test it, see what could be improved, ask us questions about your design, and maybe even get to build a second iteration of your design. I want to do a quick shout out to the team that developed this lab. I had the wonderful opportunity to work with a lot of these people. The interns were Dylan Weber, Julian Centeno, and Caroline Gillespie. And we had a resident sonar or sound engineer, Travis Sluss, who really helped us work on this lab. And it's really brought it to the wonderful lab that it is today. So now we're going to dive into some conceptual basics on sound. First, it's important to understand what sound is. The sound we hear is created when waves in a material, usually air, but it can also be water or even any kind of dense material like wood or metal, enters our ears and is detected by the inner structures of our ear. This detector in turn sends an electrical signal to our brain, which interprets the vibration, the specific frequency that it's vibrating at, as a sound we hear and what pitch that sound might be. The ear is an amazing engineering structure, and it can, and keeping your detector healthy, so all those little hair follicles that are in your ear that actually pick up these minute vibrations, is a really important part in the longevity of your life. And it's a lifelong task to keep that healthy. So you might have heard, don't listen to music too loud because you might damage your ear. So basically, if you start to abuse the ear and all of the play loud sounds in it, it will deteriorate and it will not function as originally designed. Because sound waves have energy depending on their amplitude and frequency, which we're going to see a little bit of a visual later, it's possible to damage your ear and it's possible to damage your delicate detector by putting too much energy into it, which is what happens when there's very loud sound around you. So the amplitude might be really, really large and it's sending a lot of energy into your ear. And your detector also just generally loses some of its ability as we age. So that's why, older people might have more trouble hearing than younger people. All right, so now we're going to talk about how we characterize sound waves. There are a couple different ways that we do this. Basically, in one of them is a measure of how we hear sound waves, and the other is a measure of how we mathematically detect sound waves. So if you take a look at this graphic on the left, or on the right, sorry, you can see piano keys laid out, and they have their tones and frequencies. So lower tones, lower pitches are on the left, and then it gets higher up as you go, which anyone who plays piano here might be familiar with. So you've got the C1, C2, and C3 octaves, and a series of 8 notes occupying all those octaves. And so you've got 7 of these octaves on the piano. And basically, this is the same note, but in a higher pitch each octave that you go up. So this is doubling the note's frequency, and that's kind of how we mathematically define an octave. We hear a very similar tone, but it's double the frequency. So it's basically one frequency, and then if you times 2, you get a higher octave, times 3, you get even higher of an octave, so on and so forth. And so that's what we call the same note, but in a higher pitch. Sound changes depending on how fast or slow an object vibrates to make the sound waves. And so this is what we call the pitch. It's the quality of a sound, whether it's high or low, and it depends on the frequency of the vibrations. If an object vibrates quickly, we hear a very high-pitched sound. And if an object vibrates slowly, we hear a low-pitched sound. Frequency is the number of times per second that a sound pressure wave repeats itself. So the units of frequency are called hertz, which you guys might have heard before. It's abbreviated Hz. And humans with typical hearing can hear sounds between approximately 20 hertz and 20,000 hertz. This is a really large scale, and that's why we measure a lot of the sound that we hear in the decibel system, which I will get to in a little bit. So humans with good hearing can hear from 20 to 20,000 hertz. And we've all heard that dogs can hear, a much larger scale than humans can hear. So dogs can actually hear from 64 hertz to 44,000 hertz. So this means that they can hear much higher pitch frequencies than us. And that's why if you were to blow into a dog whistle, we might not be able to hear it, but a dog would. So if you look at all the animals towards the bottom of this list, they can hear up to 100,000 hertz. This is an insane frequency. And we use acoustics to communicate on our vehicles. And we're typically, sending frequencies of maybe 25,000 hertz to about 100,000 hertz. And that's why the issue of are we affecting the marine mammals around us is so important, because if you look at the bottom of this list, it's a bunch of marine mammals. It's a beluga whale, a bottlenose dolphin, a porpoise. There are a bunch of whales that are also on the bottom of the list, like a sperm whale. And we really affect their environment by playing these loud pulses of sound. So now we're going to watch a video about noise pollution and how bad it is. And so really pay attention to, how this affects us in our daily lives. And we should really continue to understand trade-offs of how increased transportation efficiencies and new ways to develop transportation are affecting our public health. Like the example that I gave you guys, that I live right along a highway. We have to understand how we can balance all of these transportation needs with what about the people who are residential and living there. So I'm going to play this video for you guys.
This is just some of the noise that I'm exposed to. And that doesn't even include the progressive rock that my neighbors listen to every single morning. All this noise is really annoying, but it's also killing my ears. Hearing loss is the 4th highest cause of disability across the world, and it's expected to get much worse. In the US alone, 1 in 4 adults show signs of noise-induced hearing loss. One of the main reasons behind that is all the noise that's around us every single day. According to the Environmental Protection Agency, the best way to protect your hearing is to limit noise levels to 70 decibels. And experts agree that continued exposure to noise above 85 decibels will eventually harm your hearing. If you're curious about the noise levels around you, decibel readers like this one tell you exactly how much noise you're being exposed to. This one's actually fine. I ride the subway for hours every day, and it's really, really loud. But putting in my headphones doesn't really help. Smartphones cranked all the way up are about 100 decibels. This bar is 105 decibels, and according to the World Health Organization, that could damage your hearing in less than an hour. This chart shows that the louder the noise, the less exposure it takes to potentially damage your hearing.
So if any of you guys have an Apple Watch, one of the new features that they do is they actually let you know when you're in an environment of above 90 decibels for more than 10 minutes. And sometimes these things can't be helped. Like if you're taking the subway, you know, you have to get to wherever you're going. You have to stand by the train whizzing by you. So it's actually a little bit annoying for me when my watch is like, hey, get out of this noisy environment. It's going to damage your hearing. And I'm like, I can't do anything about it. But it is one of the ways that, you know, big companies and tech companies are trying to keep us aware of the kinds of sounds that we subject ourselves to every day. So now we're going to talk about measuring sound. He mentioned the decibel system, and that's really important to measuring how much power is involved in a sound signal. So it's measured in decibels. And there are many sounds in the environment, from rustling leaves, that's like 20 to 30 decibels, to a thunderclap, which is about 120 decibels. And the wail of an ambulance siren is about 120 to 140 decibels. Sounds that reach 85 decibels or higher can harm a person's ears. Sound sources that exceed this threshold include familiar things such as power lawnmowers, subway trains, and loud rock concerts. And the reason that we measure in decibels, it's kind of like a log system. If you guys have studied logarithmics in math already, if not, basically what it means is a sound that's at 10 decibels is about 100 times lower than a sound that's at 20 decibels. So it's not a linear system. It doesn't mean that a sound at 20 decibels is 2 times louder than a sound at 10 decibels. So really, you can understand the impact of being at 90 decibels and then going to 100 decibels. This is 100 times louder than the sound at 90 decibels. And that's why it gets really important to avoid these long exposure to these kinds of sounds, because it's not like we're saying, oh, the sound increased by 10%. We're saying it increased 100 times, and it's really, really loud. The power of the signal entering our ears is very, very damaging. So now I'm going to actually take a little segue and talk about sound traveling through water, because this is what I work with for a lot of my different research. So I wanted to show you guys basically a picture of sound traveling through water and the relevant decibel scale that we can hear. So if we consider zero sound in the water as this like negative 100 baseline, basically, if we have a source, I think the source is located at about 100 meters depth, and it plays some kind of signal. Right here, I've said it's an 100 hertz signal. So that's the frequency at which it's, you know, blasting out this signal. All of these yellow spots in the ocean is where a vehicle could physically be and hear that sound. Conversely, all of these blue spots is where a vehicle could be and it would hear absolutely nothing. So as you can see in air, you know, when our neighbor plays, you know, loud rock music and we're downstairs, we can hear it. There aren't really what we call these shadow zones, places where we can stand and we don't hear it, because sound travels pretty uniformly through air. However, this is very much not the case in water. If our vehicle was here, it would have no idea that there was a sound playing at this 100-meter depth. And so this is a really important concept to model as acoustic engineers and underwater engineers, because if we're trying to communicate between two vehicles and we want to hear this sound source, we have to know basically what the water around us looks like so that we can move our vehicle into one of these yellow spots. Another thing I really want to point out about sound moving through water is you've got all of these bright yellow spots, which means we can hear the vehicle we can hear the source very nicely. And it's really close, within 5 kilometers to the source. And then as it moves out, you get a lot of what we call attenuation, which means that the power level or the decibel of the sound reduces very, very much. And so we can't hear it as well. The power of the sound is not as strong. And so that's what the effect of moving through water can be, because it is a denser material or a denser fluid. The sound travels faster through it, but it also attenuates much faster through it. So we can't hear that sound, after maybe 20 kilometers. And this is a really long length scale, if normally we're only 5 kilometers away from a source in air that we hear, but in the underwater scale, the ocean's so big that we have to deal with these large length scales. So noise pollution is considered to be any unwanted or disturbing sound that affects health and well-being of humans and other organisms. Too loud of a noise can damage your ability to hear, but there are many studies that also investigate the impact of too much noise on your mental well-being, which can impact your general physical well-being. This is possibly the bigger impact of noise pollution. People living in noisy environments having more general health issues like sleep deprivation, stress, and heart and circulatory problems. The impact on younger children is particularly of concern, as it could impact their development and leave them with lifelong challenges. So this is the part that you guys are going to be studying in your lab today. How can we mitigate those effects of noise pollution? Here is a reference of a European study on the impact of noise on health. The fact is, our world is noisier than ever as we get more and more technology around us. We should continue to understand the trade-offs of new transportation conveniences, such as air travel and direct highways, versus the public health effect. This graph shows you the ways noise pollution affects people in Europe. The population of Europe is almost 750 million people as of 2 years ago. And the number at the bottom will tell you how many people are affected. For example, 22 million people become more annoyed from noise pollution, which is about 0.3% of the population. It might not seem like a high percentage, but no one likes to be, annoyed by something in their everyday life. So if barriers can be created and the noise impact reduced, then people will be healthier physically and mentally. We're going to go ahead and finish this video, and that way you guys can see the irreversible impact of how noise damages our ears and the hair follicles inside of our ears.
One of the worst things about hearing loss is that ear damage is irreversible.
Most of us are born with something like 16,000 little hair cells in our ears, and these hair cells act as sound detectors. So when sound waves pass into our ears, they send a signal up to our brain, and then our brain decodes that sound. But the brain's interpretation is only as good as the signal it receives from the ear. And when the hair cells in the ear have been damaged, the brain can't detect the sound, or the sound is distorted. You can think about the hair cells like grass. And when you're walking through a field and you walk over blades of grass, they bounce back after a few minutes. But when you walk through that field enough times, you eventually create a path. And the same thing happens with the hair cells in your ears. When loud sounds pass into the ears and at high enough intensity, they bend those hair cells and they can bounce back during a recovery period. But with enough noise over enough time, those hair cells get permanently damaged or destroyed.
When it comes to help from the government, I've got some good news and some bad news. The good news is that in the early 1970s, President Richard Nixon passed the Noise Control Act, which recognized Americans' right to a quiet environment. The bad news is that in 1981, President Ronald Reagan came along and essentially shut down the effort and left local governments to fend for themselves. The problem with that is local governments relied on federal funding to tackle noise problems. So yeah, you might be on your own on this one, but there are ways you can prevent noise-induced hearing loss. You can wear noise-canceling headphones or foam earplugs in loud environments like the subway or on airplanes. You can limit the amount of time you're exposed to loud sounds and move further away from the source of the noise. You can go into the settings and set a maximum volume on your phone to prevent playing your music too loud. So yeah, the problem's bad, but you don't have to take it lying down.
One of my favorite discoveries has been this app called Soundprint, which allows you.
So noise pollution is bad for us, but it's also bad for the wildlife surrounding us. And so now we're going to talk a little bit more about noise in the ocean, which is something that I deal with more on a day-to-day basis. So it impacts the health and well-being of wildlife. Studies have shown that loud noises cause caterpillars' hearts to beat faster and bluebirds to have fewer chicks. Animals use sound for a variety of reasons, including to navigate, find food, attract mates, and avoid predators. Noise pollution makes it difficult for them to accomplish these tasks, which affects their ability to survive. Sometimes out on the ocean, we'll perform different geological surveys, which means we look at the ocean floor. And we do this by sending a really strong acoustic pulse from the surface down to the ocean floor. And basically how it reflects back to us tells us if the ocean floor is made up of rock, sand, sediment, porous rock, kind of what type of rock the ocean floor can be. And we can find this out through sound, which is a fantastic resource. However, there are a lot of marine mammal protection acts that are in place such that we have to pulse, lower frequency sounds and build up their power level for, I think, 30 minutes to an hour before we actually perform any of the geological studies, because we're trying to basically scare wildlife away from us so that we don't damage them. And you can see here all of the different mammals that use sound for echolocation, which means they literally navigate themselves through the use of sound. And they also use it to find their prey. So it's really, really important that we always consider the wildlife and the world around us when using sound. So sound actually travels much faster in water than in air because water is so much denser than air. So sound in air travels about 343 meters per second. That's super, super fast. And that's what we call the speed of sound. So if something is flying faster than the speed of sound in air, that means it's traveling 350 meters per second. In water, the speed of sound is 1,500 meters per second. So it's 5 times faster. And it's actually dependent on the temperature of the water, the salinity of the water, and the depth of the water, the pressure levels of the water. So you can see that sound, the speed of sound changes depending on how deep we are in the water. And that's also something that we have to think about as we're navigating through the water with sound. So this is what I do. I actually spent the last couple of years investigating how we can navigate in the water with sound and better use sound to navigate our underwater vehicles. So fun fact, GPS does not work underwater. I mentioned the word attenuation earlier in this presentation, and basically that means when a signal gets so fuzzy that you can't read the signal anymore. And so if we look at a GPS satellite, it's using a light wave and it's hitting a GPS receiver. But when it hits the surface of the ocean, that signal gets so fuzzy and it spreads out so much that anything more than a couple centimeters underneath the surface of the water can't read that signal. So we have no GPS when we're underwater, which means that we have to find a new way to navigate. And what we did is we took one from the dolphins and the whales and said, okay, let's try to use echolocation. And so you can see that sound waves look a lot like this light wave. And so we use the same kinds of mathematical principles to use sound as our navigating beam instead of a light wave. So basically, if we know the time difference between a source sending out a sound and when we received it, and we know the speed of sound underwater, well, now we have a distance measurement, which is identified right here. And so this is actually where my research comes in. I'm trying to best identify where this guy is. It's called a transponder. It's our beacon for any kind of acoustic navigation. And where he is underwater is really, really important because that determines, how far away our underwater vehicle is. If we know exactly where this transponder is, then we can know exactly where this underwater vehicle is. And so that's the kind of research that I do. I use sound for navigation in my day-to-day work, and I was able to study a lot about acoustics. So I'm going to skip a couple slides just to make sure that we can talk about the lab activity that you guys are going to do. So you guys are going to use the engineering design process. And so you're going to imagine you're a team of acoustic engineers, and you're going to use the engineering process to create a sound barrier to reduce noise pollution. So pay close attention to the cyclical engineering process. We've got design, build, test, and then goes right back into learn and then design again. The components for sound and acoustics lab are as follows. You guys have an acoustic panel, a buzzer, a AA battery, the single battery holder, and some jumper wire. So you're going to try to create, with the materials around you, a sound barrier in between the buzzer and your sensor, which is your phone. And basically what you're going to do first is you're just going to measure if there was no barrier, what does that decibel reading give you? And then you're going to start putting a barrier, and then you're going to start reinforcing the barrier and see how low you can get that decibel reading. Remember that decibel is a measure of the power of the sound. So basically, you're trying to absorb all of that energy in your barrier so that your sensor, the phone on this side, does not have any of that power. And that's kind of saying that us as people behind that sound barrier, our ears aren't getting any of the power or energy of that sound. So here are the lab instructions, which are also going to be repeated in your student workbooks. And so you're going to download a volume meter app, and you guys are going to measure just the 90 centimeter decibels from between the buzzer and your sensor, which is the app that you guys will download. And then you'll create a barrier, and then you'll place the barrier between the buzzer, and you'll take measurements. Keep it at 90 centimeters. You want the distance to stay the same just so that you have a lot of constants in your experiments. You don't want too many things varying at one time. That way you can see the effect of the barrier explicitly on absorbing the sound. And then you're going to iterate your team's design a couple of times. Keep your designs less than 50 centimeters thick, just to make sure that you're not disrupting, we have to implement this in the real world, and you can't have a really, really thick barrier because it takes up valuable space. So try to keep this representative of something that we would see in the real world. And then you're going to fill out your activity sheet, which looks like this. This distance column should stay the same. This decibel level should change. And then you want to make sure that the hertz, the frequency at which you're giving the buzzer is going to be the same. Like I said, you only want to be able to change something so that the decibel level changes, and then the rest are constants in your experiment. And then you guys are going to think about how we can apply what we learned for other noise problems in our home and schools, such as how do we build an auditorium so that we can best hear the music that's coming from the stage? Or how do we build a music practice room so that no one else can hear the music coming out of the room and it doesn't disturb people around us? And so you guys are going to have this chance now to build your designs, and then we will reconvene. And you guys will get to ask some of our college mentors and staff some questions about your design choices, any questions you might have about the properties of acoustics. So if you guys are interested in topics today, definitely look into noise pollution, architectural acoustics, musical acoustics, and then I'm going to throw underwater navigation in there as, kind of a throw to what I do every day.
Well, I'm going to hop in here and say thank you so much, Lauren, for leading such a great introduction. I think all the students are ready to roll and build their sound barriers. I want to say our breakout rooms are going to open right now. I'm going to share my screen. We will have an hour for you guys to build. We'll be back in the main room at 11:30. And I hope that